So problem number 11, this one about the springs and the weights. So let's see, Mary Jean is experimenting with weights of 100 grams attached to a spring. She records the weight and length of the spring after attaching the weight. And here we have the following table, guys. Okay, so let's answer question A. Write the general formula that represents the length of the spring if n weights are attached. Okay, so here we can see that the length, the successive lengths follow an arithmetic sequence, right, in which the difference is 4. 45 plus 4, 49, 49 plus 4, 53, and so on. So basically we're talking about an arithmetic sequence, right, in which the first term is 45. Maybe we should write, instead of U1, we should write L1. Okay, I don't want you to understand, guys, that you should always represent the first term in a sequence with U, as such as in the book, right? So for some other purposes, maybe another variable is desired, such as length. The length of the spring with one weight attached is 45. And then the length of the spring when two weights are attached is 49, and so on. So the sequence is clearly 45, 49, etc. So let's write a general formula that represents the length. So basically we want to find the nth term of this sequence. We know the first term, and the difference is 4. So that's it. According to our booklet, if we follow the formula, that should be the first term plus n minus 1 times the difference. So we should have the following. That's it. That solves the question A. Let's move down. Number B, well, letter B, calculate the supposed length of a spring if a 1 kilogram weight is attached. So a 1 kilogram weight is equivalent to 10 weights. 10 weights of 100 grams, which are the ones that we actually are working with. So basically we're looking for the length of the spring if 10 weights of 100 grams are attached. And this is obtained very nicely using our previous formula, this one. All you have to do is plug in the values, and that's it. Letter C. Explain any limitations of Mary Jean's experiment. Well, the limitations are very obvious, right? I mean, the length of the spring, once you lengthen it quite a lot, like for example, at first it's very compressed, right? And then this is the spring, and then it's gonna become like this, and then like this, and then like this. So you see what I mean, right? At some point, eventually, the spring will be completely, let's say, the wire of the spring will be completely in a vertical wire, so to speak, and even much before this. And at this time, guys, this sequence may stop working because the properties of a spring, and this is physics that I'm talking to you about, the properties of a spring only are conserved for let's say short, not short, small forces that you put on them, small forces. In this case, the weights that you're attaching to the spring. So the spring conserves its properties only for small forces or medium-sized forces. If you apply a lot of force, you're gonna basically deflect or completely break down the spring, and then it's not gonna go back to its original shape and so on. So those are the limitations of this experiment. there are limitations due to the internal molecular configuration of a spring, and that's physics, right? That's actually physics. Okay, and then the last letter, letter D. If the spring stretches to 101 centimeters, what is the total weight that was attached to the spring? So now we know that the length is 101 centimeters. So I need to plug that into, once again, into this formula, and in here, 101 centimeters should be equal to this. And now, and when we solve for n, we'll be knowing how many weights of 100 grams we hanged from the hung. I'll check that in a moment. We uh we hanged from the spring. Okay, that's it. That's how you solve it. Simple. And it's gonna be 15, by the way. It's gonna be 15. Okay, so that's how you solve this problem.